Alright, in this video we'll be going through the 2021 Waves exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you've completed the question or get stuck, unpause the video to see how I go about getting the answer. Two loudspeakers are connected to the same signal generator, which is set to make the loudspeakers vibrate at a frequency of 8.95 times 10 to the 2 Hz. Which corresponds to a wavelength of 0.381 meters in air. The teacher makes sure that she wires the speakers so that they move in phase. A student uses her phone to measure the sound intensity at point A, which is equally distanced from both speakers. She moves the phone towards B, noting that the sound gets quieter and then louder again. The diagram shows below the setup. Determine the distance the student will have to move the phone to find the first quiet point between A and B. If we see our situation where we have our two speakers, point A is going to be a loud spot because this is our n is equal to 0 antinodal spot. Okay, and point B is also going to be a loud spot, and therefore this is our n is equal to 1 spot. Okay, and so therefore the place in which the sound gets quiet is in between, and this is our n is equal to 0.5 antinodal line. Okay, and so therefore we know that n lambda is equal to dx all over L. Now in my second interference video, I go through the derivation of this formula, so you can go check that out if you don't know where it comes from. But we are given our wavelength right here. I just found our n value. Our d value is the separation between the two sources, and so that's 1.5 meters. Our L is this distance right here, and our x value is what we are trying to find, right? That is this distance right here. Okay, and so now we can rearrange for x, and we get n lambda L all over d is equal to x, and therefore plugging in our numbers 0.5 times our wavelength of 0.381 times our distance L of 25 meters all over our distance d of 1.5 meters, and this gives a distance of 3.175 meters. There we go. Explain how superposition causes the sound intensity to change when the phone is moved from A to B. Alright, so if we draw our situation where we have our two sources right here, and this is A, and over here is B, okay? Because A is our n is equal to 0 antinodal line, this means that when the waves meet at A, there is going to be no path difference between the two waves. And therefore, because there's no path difference, obviously our path difference is equal to 0. And so therefore, because our path difference is a whole number, the waves are going to meet in phase and therefore constructively interfere and produce a loud spot, which is what it said up here. As the phone is moved from A to B, the path difference between the two waves begin to increase. So what that means is when the phone was at A, the path difference was 0, but then as the phone moves from A to B, it begins to increase to 0.1, then 0.2, then 0.3, right? These are all non-whole numbers, okay? So as the path difference begins to increase, this obviously introduces a phase difference, and this results in mild destructive interference, and therefore the sound gradually begins to decrease in volume. Right in between A and B, the path difference is half a wavelength, and so therefore the waves from the two speakers are exactly 180 degrees out of phase, and so at this point pure destructive interference takes place, and this results in a quiet spot. As we move from the middle of A and B towards B, our path difference begins to increase again towards a whole number. However, as the path difference is still not a whole number, this is still going to result in minor destructive interference, and so it's still not going to be quite as loud. However, the sound is gradually getting louder as we approach B. Once we are at B, the path difference is now a whole number of wavelengths, and therefore this again results in pure constructive interference, resulting in a loud spot. And you can write that in. Describe the difference in the pattern of loud and soft sounds the students would hear as they walk along A and B if the speakers were further apart. Give reasons for your answer. So what this means is that, again, if we have n lambda is equal to d sine theta, if the speakers were further apart, this means that our d value would increase, okay? So our d value is going to increase. And so therefore, as our wavelength of the sound is not going to change, if our d value increases, therefore our theta value must decrease. And so therefore the loud spots are going to be closer together. Another way you can look at this, you can say that n lambda is equal to dx over L, as our L value is going to remain the same because that's the distance from the speakers to the students. Our lambda value again is not going to change, and our d value is what has increased, and therefore this must cause a decrease in our x value. And again, remember our x value is the distance between maxima, okay? The teacher also wants to demonstrate beats. With speaker 1 making a frequency of 895 Hz, she connects speaker 2 so that it will make an equally loud sound of frequency 890 Hz. Explain why the students hear a note that regularly changes in loudness and determine the frequency of this beat. Okay, so we know our beat frequency is equal to F1 minus F2, okay? Let's say our F1 is equal to 895 Hz and our F2 is equal to 890 Hz. Okay, so F1 is 895 Hz, F2 is 890 Hz. Okay, and so therefore our beat frequency is going to be equal to 895 minus 890, and we take the absolute value of this, and this gives a beat frequency of 5 Hz. There we go. So beats are caused by two sources that have very, very similar frequencies, but because these two sources don't have the exact same frequency, if we observe the two sources from a fixed position, due to the fact that the two sources have different frequencies, they will continuously come in and out of phase. And so when the two sources are in phase, the path difference is a whole number of wavelengths, and therefore they are going to constructively interfere, therefore producing a louder sound. However, when the two sources are out of phase, as the path difference is a non-whole number of wavelengths, and therefore this results in destructive interference and a quiet sound. Okay? And so because the source is continuously coming in and out of phase, what this results in is a sound that changes from loud to quiet, loud to quiet, loud to quiet. And this results in sort of a beating sensation. And you can write that in. Describe the changes to the frequency of the beats the students will hear as the teacher slowly increases the frequency of speaker 2 from 890 Hz to 900 Hz. Speaker 1 remains at the frequency of 895 Hz. So we can call the frequency produced by speaker 1 F1, and we know that stays at 895 Hz the entire time. However, F2, which is the frequency produced by speaker 2, starts initially at 890 Hz, okay? So let's start with that. When we have this as the scenario, this is essentially the exact same scenario that we had up here, and therefore the students will hear a beat frequency of 5 Hz, okay? However, as the teacher begins to increase the frequency of F2, we can imagine, because our beat frequency formula is equal to F1 minus F2, if our F2 gets larger and our F1 remains the same, therefore our beat frequency is going to decrease, okay? And it's going to continually decrease until F2 is equal to F1 at 895 Hz, okay? And therefore when F1 and F2 are equal to each other, therefore our beat frequency is going to be 0 Hz, and therefore no beats are going to be heard, alright? And then from here, if we increase F2 even more, all of a sudden, our F2 is going to be larger than F1. And therefore, again, as our beat frequency is equal to the absolute value of F1 minus F2. Now remember, the absolute value just makes the answer positive, okay? So now if our F2 is larger than F1, our beat frequency is going to start to increase again, and we're going to start hearing beats once more. And then once F2 is equal to 900 Hz, and again F1 still remains at 895 Hz, therefore our beat frequency is going to become 5 Hz once more, okay? And so you can write that in. The speed of sound in air is 341 meters per second. Mark makes a sort of didgeridoo using a piece of plastic drain pipe 1.2 meters long. Mark vibrates his lips against the pipe, making the air vibrate in the tube, and also blocking the tube at the end he is blowing into, so that one end is closed while the other is open. Calculate the wavelength of the lowest note that Mark can make with his didgeridoo. So this is a case where we have a closed end and an open end, and we know that this results in a node at one side and an antinode on the other. So the lowest note is the one with the lowest frequency, okay? And so we need to find the one with the highest wavelength, right? Because we know V is equal to F lambda, and our velocity of the wave is not going to change. And so therefore, in order to get the longest wavelength, we need the first harmonic. And so the first harmonic is when we have our length is equal to 1/4 of the wavelength, and therefore 4 times the length is equal to our wavelength. The drain pipe is 1.2 meters long, and so therefore 4 times 1.2 is equal to our wavelength, and this gives a wavelength of 4.8 meters. There we go. Some of the richness in the tone of the didgeridoo is caused by the presence of overtones. In the space below, label the positions of nodes and antinodes that the first and 2 overtones will produce. State how the frequency of these overtones relate to the lowest fundamental frequency of the pipe. Alright, so we know that for a closed and open-ended pipe, our first overtone is equal to the third harmonic, and therefore this is 3 times the fundamental frequency, which we can call F1, okay? Our second overtone is the 5th harmonic, and this is equal to 5 times the fundamental frequency again, which we can call F1. And as you can see, once again, we can see that in a closed and open-ended pipe, we cannot produce even harmonics, right? We skip the second and fourth harmonic in this case. And so let's make this top one the third harmonic and this bottom one the fifth harmonic. Okay, so for the third harmonic, again, we have a node on this side and an antinode over here, and we will have an antinode over here and a node over here, and this is our classic fish shape, like so. And now for the fifth harmonic, again, we have a node on this side, antinode over here, antinode over here, node over here, node over here, and antinode over there. Again, these should be evenly spaced as close as possible. And so we get this shape right here. There we go. Although marked slopes vibrate at many frequency, the pipe resonates only at certain frequencies. Explain how the sound waves travel in the pipe to produce only these natural resonant frequencies. Alright, so we have our closed-end and open-ended pipe. As the sound waves enter the pipe from Mark's mouth, they will reflect off the closed end and then therefore go through a 180 degrees phase change. And when this happens, it will interfere with the oncoming wave and therefore destructively interfere as those two waves are 180 degrees out of phase, therefore producing a node. However, at the open end, there's going to be no phase change taking place, and therefore the waves are going to interfere with each other, producing an antinode. Therefore, because of this, the only wavelengths that can fit in this pipe are those that always have an antinode at the open end and a node at the closed end. Any other wavelengths will not fit. And so because of this, we are only allowed odd multiples of 1/4 wavelengths, okay? And so odd multiples of 1/4 wavelengths is 1/4, 3/4, 5/4, 7/4, etc., right? Notice that if we have even multiples of 1/4, let's say we have 2/4 or 4/4, we notice that this can be simplified to 1/2 and to 1. And therefore, in order for this to take place, in order for us to have half a wavelength and 1 wavelength, we must have successive nodes or successive antinodes, okay? And again, if you don't know what this is, I go through this in my standing waves video. I think it's the second video in my waves playlist, okay? However, in this, as we can see, just based on this first harmonic, we do not have successive nodes or antinodes. We just have 1 node and 1 antinode. So therefore, we are only allowed odd multiples of 1/4 wavelengths. And so all these reflections within the pipe will produce a standing wave with fixed points of constructive and destructive interference, which are our antinodes and nodes respectively. As the energy of the pipe begins to build, meaning we are adding energy at the natural frequency, the pipe begins to resonate, right? That's our concept of resonance coming in from our simple harmonic motion. We are adding energy at the natural frequency. The frequencies that aren't able to produce standing waves don't add energy at the natural frequency and therefore are not able to resonate. And you can write that all in. As Mark keeps blowing into the pipe, the air warms up so that the speed of sound in the pipe increases. Explain how this will affect the resonant frequencies of the sound that the pipe produces. So therefore we know our V is equal to F lambda. Because our wavelength is determined by the length of the pipe, and the length of the pipe is unchanged, therefore our wavelength is going to be constant. Okay? And therefore, obviously, it's not going to change. So therefore, if the velocity of the wave increases and our wavelength is constant, this results in the frequency must increase. And so the frequency for all resonant frequencies will increase. And so you can write that in. Susan is watching a Formula 1 car race. As the car goes past, she hears a familiar sound of the engine change due to the Doppler effect. A car approaching Susan at a speed of 44.4 meters per second, and Susan hears the engine frequency at 6.5 times 10 to the 2 hertz. Show that the frequency heard by the driver is 565. Alright, so we know our Doppler equation is F dash is equal to our source frequency times the velocity of the wave all over the velocity of the wave minus the velocity of the source. Again, we're using minus in this case because the car is approaching Susan. Again, if you don't know where this formula comes from, I go through it in my first Doppler video, and that's on the Waves playlist, so you can go check that out. What we are trying to find is the source frequency because that is what the driver is going to hear. The reason why the driver is going to hear the source frequency is because there is no relative motion between the driver and the car. As the driver is in the car, the driver is also moving at 44.4 meters per second. And so there's no relative difference between the velocity of the driver and the velocity of the car. And so the driver will hear no Doppler effect and will hear the true constant frequency. So we can rearrange for our source frequency and we get F dash times the velocity of the wave minus the velocity of the source is equal to our Fs times Vw. And therefore we can divide by Vw on both sides. Now plugging in our numbers, we're given our perceived frequency as 650 Hz times the velocity of the wave, which is given as 341, minus the velocity of the source, which is 44.4, all over the velocity of the wave, which is 341. And this gives a source frequency of 565.37 hertz, which we can round down to 565 hertz. And as you can see, that is the value that we're trying to find. Explain why the motion of the car causes Susan to hear a different frequency to that which the driver hears. So this is adding on to what I said in the first part of this question. If we were to draw the source, which is the F1 car, as a dot, okay, and we look at it from the bird's eye view, and we have Susan over here. Okay, so this is Susan, and this is the car. As the car moves at 44.4 meters per second, okay, it's going to produce wavefronts. But because the car is moving to the right, it's going to catch up to the wavefronts that it emits. And so what this results in is the wavefronts in front of the car being bunched up, and the wavefronts behind the car being spread out. Alright, so the car is catching up to previously emitted wavefronts. And so what this results in is Susan is going to perceive shorter wavelengths, because once these wavelengths reach Susan, they're still going to be bunched up. And so therefore Susan is going to perceive shorter wavelengths. Okay, and as v is equal to f lambda, as the velocity of the wave does not change, if Susan perceives shorter wavelengths, she is going to perceive a higher frequency, okay? And that can be seen up here. Susan hears a frequency of 650 hertz, however the driver hears the true frequency of 565 hertz. Alright, and the reason why the driver hears the true frequency is what I said in part A. Because the driver is in the car, there is going to be no relative difference between the car's velocity and the driver's velocity, because the driver's in the car, and so he's also moving at 44.4 meters per second. And so he's going to perceive the true wavelength of the sound, and so therefore he's going to perceive the true frequency. And so you can write that in. After the car has passed Susan, Susan hears an engine frequency of 500 hertz. Susan wants to know whether the car is still traveling at 44.4 meters per second. By assuming the true frequency of the engine has not changed, determine whether the car has changed speeds. Alright, so we know our Doppler equation is the perceived frequency is equal to the frequency of the source times the velocity of the wave, all over the velocity of the wave plus the velocity of the source. Again, using plus this time around because the car is now moving away from Susan. Now again, if you don't know the reason why we use minus on approach and plus when the car is moving away, I go through that in my first Doppler video, and that's on the Waves playlist, so you can go check that out if you don't know. Now what we want to know is whether the car is still traveling at 44.4 meters per second, and so therefore we need to find the source velocity. So we can rearrange for our source velocity, and we get VW plus VS is equal to Fs times VW all over our perceived frequency. And therefore, Vs is equal to Fs times Vw all over our perceived frequency minus the velocity of the wave. Now plugging in our numbers, our true frequency is 565 hertz times 341 all over 500 hertz, which is the perceived frequency that Susan hears now, minus 341. And this gives a source velocity of 44.33 meters per second. Alright, and so therefore, as we can see, that is not the same value as 44.4, and so the source velocity has changed. In the marking schedule, there is another method in which you can plug in 44.4 into this equation and see if the perceived frequency is different, okay? And if you do that, what you will get is a perceived frequency of 499.9 hertz, okay? And then from here, you can round to 500 hertz. And so you can say that when we plug in 44.4 into the source frequency, we get 500 hertz. Therefore, the velocity of the source does not change. Now, I think this is kind of dumb because although the source velocity changes, we can see it doesn't change by that much. It changes by 0.07 meters per second. Okay, 0.07 meters per second can explain this 0.1 difference in frequency, okay? So, if you use this method, my humble opinion, it is not correct to say that the source frequency is the same, because even when you plug in the numbers, we get a different frequency to 500, even if it's by a small amount, okay? I think NCEA just did that because they wanted to give people the mark, because maybe a lot of people did that method. But anyways, carry on. Susan knows that the car accelerates. Susan knows that as the car accelerates, the frequency of the sound produced by the engine increases. After the car has passed Susan, it accelerates away with an increase in engine frequency of 10%. When the car's speed has increased by 10%, will the frequency Susan hears be higher due to the higher revs, or lower due to the Doppler effect? Justify your answer using equations or simple calculations. Alright, so if the new frequency is 10% higher, therefore the new source frequency is going to be equal to the original source frequency, times 1.1, and therefore this gives a new source frequency of 621.5 hertz. Alright, so now the engine is producing this frequency right here. If our source velocity is now 10% more, we again times our original source velocity by 1.1, and therefore this gives a new source velocity as 48.84 meters per second. Okay, so now what we can do is use the Doppler equation, again using plus because the car is moving away from us, and we can plug in our new source frequency and our new source velocity, okay? Alright, and now this gives a frequency of 543.64 hertz. Alright, and so as we can see, Susan will hear a higher frequency. Alright, and with that we are done. See you.